title is LLM agent, tool usage, and large action models. We call it labs. So first, like why we study LLM agent. So we already have like a lot of great LLMs nowadays, like GPT-4, Gemini, Llama 3. But most of them currently can only chat with you. And they cannot get, for example, they cannot get the most up-to-date information, and they can, more importantly, they cannot do things for you. So that's the actually here I have examples here. It's fine. Yeah, just some demo video to show why we need animation. So basically, if you ask ChatGPT like, what is the current president of the United States, it will tell you who is running for the president for 2024. It will say it's Biden. You cannot say like it's you cannot get the most up-to-date information. But if you just add a simple API like search API, it can accurately tell you that Kamala Harris is running for the president. And yeah, so basically there are a lot of actually potentials for large language model agents. I think here a lot of people are already familiar with them. Like we can have some work agent, personal agent, or some even creative agent to help you to build some innovative things. And there are a lot more, like code agents, which can help you write code or do some software engineering tasks, which will be presented by Wira in the next talk. And a lot of other like web agent, OS agent stuff. So there are a lot of potentials here. So right now I can give a very quick overview to what is agent to the friends who are not quite familiar with this domain. So basically, at the core, the AI agent, of course, there is a large language model inside as the brain. So basically, but in contrast to just chat with them, the large language model has to interact with some kind of environment, for example, your computer or some web browser. So basically, the language model will generate some executable actions, and then we will apply this action to the environment, and the environment will like send back to the new observations after taking the action back to the model, and it will generate the next action. For example, if we give a task instruction like place an online order for a new pair of black running shoes for me, the output, the response, could be like a sequence of action to place this order, just like what a human do. And the final response, final observation is that your shoes will be like connected to your grass or something like that. Yeah, and inside of this agent framework, there are several like key modules. For example, the action parser, which parses the raw text output from the model to some executable actions, like some functions or API calls. And there are also some modules like memory, which stores the previous trajectory or previous observations, etc. And also, of course, we have to do some careful prompt engineering to prompt the model to be able to serve as an AI agent. And a lot of like works have already done in the agent framework domain. For example, one of the most famous one is called the React framework. Very simple and intuitive. So basically, after we receive observations from the environment, we prompt the model to think before we take actions, and we also provide it with a few short of examples to better enable the agent to decide what is the next proper action to do. And also like a lot of other great frameworks, just like K1, etc. But in this talk, we will like focus on training the model itself, rather than simply rather than like investigating talking about the agent framework. So because we think that no matter what kind of framework we're using, at the core or at the back end, we still need to rely on a powerful large language model to make the decision, to do reasoning and thinking. So basically we will talk about how could we train such kind of good models which can take actions. So first, what is large action model? It's basically trained by a lot of agent data from a wide range of domains, and we have some foundational large language models. And after we train them together, we finally enable the agent to make the ability to make the decisions, like do some proper function calling, planning, reasoning. So here is a very kind of overview for agent frameworks. Here we can see around the agent in the center, there are four different capabilities, like the memories, planning, action, and the tools. So for the planning, it's basically the use of techniques like chain of thought, or critics, reflection, this kind of techniques to help the agent to do some long-term, long-horizon planning for what should be done in sequence to finish some task. And for the action and the tools, these are basically some APIs that the agent could call to finish some action. So, for example, the tools could be get some calendar, or call some calculator to do some math operations, or call a code interpreter to running some Python code or any kind of code on the backend. So we focus on the tool usage and function calling in this talk because we believe that this is kind of currently one of the most important capabilities and one of the most fundamental capabilities for agent. Because the tool usage is basically the bridge between the model and the environment. And actually, many of the recent models already upgrade the ability. Just like the Llama 3.1, they emphasize this function calling ability. And like this code, Cloud 3.5, they also all of them emphasize a lot on the tool usage ability. Because many developers actually want a powerful model which can do proper function calling to finish their own workflows. Also, like GPT Store is basically also a collection of function calling models with function calling agents. So basically, someone gives some prompts for how to using their own APIs, and they basically can wrap up them as one of the agents in the GPT Store. And here is one typical example of like a weather agent. Okay, so this is the user say, I want to know the weather in Palo Alto, and after a lot of things to be done in the backend, the agent finally tell you like what is the weather today. So what's happening in the backend? So actually there are a lot of behind the scenes. There are several different steps. So the first step, you have to provide the agent what are the proper available functions to call. For example, you probably have already provided the agent with a lot of functions like the check stock price, get weather, get some news, etc. It has to decide what is the proper function to call and what is the proper arguments to finish to answer the user query. And after the model generates the function call, we will execute the APIs in the backend, and the API after the API calling, it will return some results. Back we will concat the results with all the previous chat history and do the summarization, and finally the user will see like what is today's weather. That's what happens behind the scenes. So yeah, that's the talk. Okay. But there is actually a lot of challenges for this even very simple task. For example, how could we understand users' intention and accurately select proper tools? So because when the developer expand their like workflows, they will probably need to call have multiple APIs in the API list, And we cannot control what's the user intention. The user intention could be varies a lot. So the most simplest scenario is that with only one user's query contains only one intention, such that we could like just return one tuple from a list of APIs. But a more challenging one is that the user's query contains multiple intentions. For example, the user may just ask like, what is the weather in Palo Alto? And meanwhile, I also want to know the ticket price from the New York to San Francisco, something like that. So one query contains multiple intentions. So the model needs to identify how many intentions there and to return the correct number of tuples from the list of APIs. And another situation is that the user query might not be like suitable or lack some necessary information for the model to address. For example, the user may ask, how could I be rich? There's no like proper APIs to achieve that. So in that sense, the model should identify that we should not answer this by calling any of these APIs. So this is called relevance detection category. And another challenge is that how could we optimize the workflow efficiency and the flexibility? So many large closed source models like GPT-4, they perform pretty well, but they usually have high latency and cost. And also the prompting is the only way we can using them to our own workflows. So if we have to basically, the only thing we can do is to revise our prompt to make the agent, to make the model, attempt to make the model learns how to use our APIs. So there's no other ways to fine tune their model. There's not a principal way to fine tune their model. So we basically need some better open source and customized models. But the situation is that there's very few related datasets that is publicly available for function calling. And the quality of the public datasets also cannot be assured. So we basically need some smarter, stronger, and open source function calling models. And we also need more high quality datasets in this area. So that's why we bring our XLAM. So this will basically release a family of open large action models from tiny to large, from 1B, 7B to 8x7B or 8x22B. So basically tailored for different use cases. For example, the 1B model and 7B model could be readily deployed on your personal devices, like your phone or your personal computer. But the performance is relatively like slightly lower than our large models. So here is an overview of the performance on the function calling benchmark, on the function calling benchmark. So basically, our largest model always was the top one on this leaderboard for a long time. Actually, their leaderboard updated very frequently to incorporate many live user queries, which are totally unseen by our model, but it's currently still like ranks top one on the leaderboard. Surpass all the like GPT-4, cloud, etc. And our 7B model can achieve like similar performance to GPT-4 in terms of function calling, and the 1B model like achieves similar performance to GPT-3.5. So we can see a lot of potentials here that using much smaller models can achieve very strong capabilities in this most fundamental like agent usage domain. So here is very general overview for the training pipeline. Basically, there are already certain some of the agent like data sets on the internet, but they varies in the data format or they vary for the action space, etc. So our first job is to unify all the agent data sets from different environments together with a standard like representation for the action space, safe space, etc. And after that, we did a lot of like work on the quality verification to filter out those like low quality data because currently I think most of the agent data sets are also collected by like models rather than annotated by human because the agent data set is a trajectory which is pretty hard to annotate by very expensive human. So we have to do a lot of quality verification, and after that we do a bunch of data augmentation, data mixture, model training, etc. And one core technology we use here is the data synthesis. So basically, how to synthesize high quality function calling data to better invoke our base models and function calling ability. So that's the focus of this talk. So data synthesis, and this technique is actually presented in our recent paper called APIGen, automated pipeline for generating verifiable and diverse function calling datasets. All the models and datasets have been open source right now. So here's a brief overview for the pipeline. So basically, first collect a bunch of API libraries on the internet. And we also have some seed QA dataset, and our prompt library to prompt the model to generate similar queries and corresponding function call answers. If we just look at this one, it's very similar to simulate distilling like a large models, but later I will choose like how it differs from the simple distilling, and it's for all of this data structures, we use the JSON for structural inputs and outputs for all the representations. Because for APIs, like there's some Python APIs, REST APIs, or Java APIs. They are a very diverse format, but we can always convert them to some JSON, to a standard JSON format, and then convert them back to the. We can write some converter and inverse converter to convert them back. So I think that using a standardized way to represent all APIs can better help us help the model to learn like what is the real like reasoning or planning inside, rather than like overfit into some formatting issues. So basically, the API is some API name, description, parameters, etc. And the function call is basically also similar to the OpenAI function call format. And the generators, the model's output is basically the synthesized query and also a list of answers, also basically a list of function calls. So here is the core of our core insights for our data synthesis pipeline. So we have to do some very rigorous or multi-stage data verification for the data generated by large language models. So we have for each of generated data point, we go through like 3 stages of checker. The first is format checker, basically check like whether the generated format meets our requirements. And in this stage, we can also remove some hallucination issues. For example, if the model generated some function calls that doesn't appear in the provided API list. So actually, this format check is very powerful to filter out this low quality generated data. And after the format checker, we send the results to the execution checker to really run the API in the backend. And after get the execution results, all the results and our queries will be sent to another like LLM large language model judger, which will tell like whether the final execution results aligns with the user's intention. Only the dataset that pass all 3 stages, it will be regarded as a verified data point, and will be added to our seed dataset for further generating more diverse data. So basically here the key idea is verification by execution. I think this is so basically for this domain, for the agent domain, it's quite different from other domains like chat competition or because for that type of method, there is no very good ground truth or there's no very objective measurement for what is whether it's good or not for the synthesized data. But in the function calling domain, we actually could run the generated generate the actions by execution. So which can this feedback is very important for the LM judger to determine whether this data is good or not. So this is basically the key insight. And when design this generation framework, there are several principles. The first one is diversity. We want to ensure the generated user queries are very large diversity, and also our API is a large diversity. So we achieve this by using like different prompting library, and also we use sampling strategy. So basically, every time of generation, we randomly sample a random number of APIs from our API pools, and also randomly sample a random number of examples, fictional examples from our seed QA datasets. So basically, all of them are randomized, which can kind of enhance the diversity of datasets. And for quality is we first have to ensure that all our API libraries are of high quality. They should be executable, and also the generation quality, basically through the multi-stage verification. And finally, is the scalability. Is that we use unified JSON format. So if in the future, if we have some new APIs come in, we just need to write a simple converter to convert their format to the JSON format, and then we can simply like generate corresponding data for the APIs, which can ensure the scalability. So there are some examples for the APIs. So basically, collecting those APIs are most time-consuming part because how to collect this kind of high quality and executable APIs are very tedious work. So we did a lot of filtering on this part. Here's basically some examples for the Python function APIs and the REST APIs. So for all the APIs we collected, we do like API quality filtering, accessibility testing, and also downstream rewriting. So with the downstream rewriting, it means we have to make sure we provide all the necessary information for the model to learn how to use this API. Yes, this is an overview for the API sources. We collect like more than 3,000 of APIs from diverse sources with different categories, and all of them are executable and with good doc strings. And for the prompting library, it's also like we designed a few of them to prompt the model to synthesize such kind of data. Okay, so first let's see whether the strategy for the multi-stage verification works. So we prompt a few of the pretty powerful open source models to synthesize such kind of data set, and we prompt each model to generate 40,000 of data, and you can see for the weak models, its pass rate is only like 34%, meaning that most of the generated data are actually of very low quality. And even the strongest model like DCP2 chat, its pass rate is only like 84. So it's meaning that no matter how carefully we design the prompt or how carefully we collect the APIs, the model still will hallucinate or generate some like random low quality data during the data synthesize procedure. And from this different stage statistics, we found that the failed execution part is actually takes a lot for the relatively weak models. It basically means that if we prompt some weak models to synthesize such kind of data, most of the generated function calls are actually not even executable. So we can imagine that if we use this kind of data set to train our model, how bad it will. So we will, here I mainly use two examples models for the ablation study. like using the 1B and the 7B models. So, and the benchmark is the both the function point leaderboard we just mentioned, and they contain a lot of like test entries. And the most recent one also contains many live user queries to test the function calling ability. So this is some older results, but never mind. Our 7B model actually performs pretty good on this leaderboard, and even the 1B model performs very well. It's actually the only like model, the tiny size model, which is less than 6B on this leaderboard, but it still like outperforms many other models like G3.5, etc. So why? Here is a ablation study from our experiment. So if we only use our verified datasets to train a model, it can achieve very good performance. However, if we remove our the last semantic verification checker, meaning that if we add some low quality data back to the training set and train our model, the performance degrades by up to like 9%. And if we like add even more low quality data who failed the execution checker to the training set, you can find that the performance degradation is even more. So this basically means that the low quality data indeed like influence our model performance a lot. And we can also observe that the smaller model is actually more sensitive to the quality of the data. So if we want to, because currently there's a trend that people developing like on-device or smaller language models. So we have to better to control the quality of their training data to ensure the model capability. Yeah. So even without this high quality data, our model is basically with the entire like training set, the model performance is just very normal. But with such kind of high quality data, even smaller models can achieve can match the large models capabilities. Yeah, so that's why we study we also study like this tiny size or small size models. There are a lot of potential to deploy these models, these customized models which can call API on your personal device, just like the Apple Intelligence, which will be released in a few months. So like the new Siri, behind the new Siri, I think the function calling is one of the key capabilities. And our work basically shows that the small model is able to do such kind of work on your device. Yeah, so basically, currently all our models and the datasets are public released. We also provide some quantized versions which can be readily deployed on the device to use. And for the future direction, we could here just list a few. Like we could further reduce the latency and of inference, because the latency is really important for agent use cases. We don't want for example, just ask a single query. The model will think like O1 think like 7 seconds or 10 seconds to tell you what is the weather right now. Yeah. So we definitely need to reduce the latency and inference time for this type of personal assistant on our personal device. And we can also investigate some other techniques, for example, how to better embed the knowledge of users' APIs into the model, like using some like pre-training, continuous pre-training techniques, etc. There are a lot of things could be optimized here. And we can also like collect more high quality data sets for diverse usage scenarios. And even more with this pipeline, people can easily like generate their own business API usage, like the training data sets for using their business APIs, and then fine tune their models to customize a small model to use their own companies APIs. That would be like a very promising direction. And also we could probably still extend this data synthesis pipeline beyond just simple function calling. You can do like web agent, OS agent, or SW agent domains. So the core idea here is basically the same. We have to ensure the data quality and verify by execution. Yeah, there's actually a lot of more insights in the paper, but I will not cover in detail in this talk. So if you have any questions or anything you want to discuss, feel free to jump in.